Hello and welcome to Chem 400 Office Hours. Let me know. It's weird that it was Thanksgiving week last week. We didn't have office hours. Anyways, I'm here. I'm ready to hit up any questions you may have. So let me know what you're struggling with, and we will get into it. Oh, so actually, I had it muted. Um, that's why you couldn't hear anything. Um, because for a brief second, my wife was changing a diaper. She had to come in and grab something, so I muted the mic, so we wouldn't have baby squawks up in the stream. But now she's gone. But I had forgotten to unmute it, so that's why. Oh yeah. No, it's here. And actually, I can unmute my mic because as you can, I don't know if you can see, but wait, no, back there, right there, that's the baby changing station. So I muted the mic and muted the video because we didn't want a baby with a diaper change going on live on YouTube. Less than professional. So what I would definitely say when it comes to preparing for exam 4 is the 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 best way. So the best way to prepare for it is working as many problems as possible. Um, Oftentimes, students fall into a trap of thinking like, "Oh, I'm gonna rewatch all the lectures, and that'll get me ready for the exam." And the reality is in an exam setting, you're not being tested on your ability to watch a lecture, follow along, take notes. You're being tested on your ability to read a problem, assess how to find what you're trying to find from the given information, and then do the necessary logic, math, what have you in the problem to solve it. And so the best way to prepare, I've had students, tell me like, I didn't do well in the exam and I don't understand what happened. I watched every lecture 4 times through, and it's because watching lecture is like the beginning, but to like introduce the concepts, to know what's going on. But what gets you ready to take the test is doing problems. So the problems in the back of the book are excellent. They have a whole range of difficulty, from introductory to challenging, and I think working those once you've done the problems in the back of the book, because you may have, you can take the concepts that you struggle with, and hit up like Google the topic Gen Chem worksheet, and the internet is literally full of PDFs created by professors that deal with that material. And so as many new takes and different problems you can expose yourself to, the better you're going to be prepared to take the exam. So that would be my my advice. Make problem solving the focus of it, and do it consistently over a period of days. Like if you have 8 hours to study, you'll be better doing 4 2-hour study sessions over 4 days than doing 8 hours all in one day. So that'd be my recommendation. Let me double check just to make sure. Yeah, so so exam 4 is going to cover the end of chapter 7. Through hybridization. And hybridization is the cutoff. All right, cool. Julia, let me hit that question up. So, sorry. Well, sorry. We have two Julias up in the chat at the same time. Julia Nunn, let me hit up the hybridization of the. Let's see. Determine the molecular geometry of the central atom of SO3 -2. So, sulfite. So first thing we have to do, if we're going to determine our molecular geometry, is we got to draw the Lewis structure. So we need to total our electrons. Sulfur has 6 valence electrons. Oxygen has 6 valence electrons. Because, I don't know why. Well, actually, I do know why. Superscripted a 3 there. Because we have 3 oxygens. So we have not just 6 electrons, but 6 times 3, right? So total of 18 there. Plus we have our charge of -2, which means that there are 2 additional electrons in this molecule that wouldn't be there otherwise. So let's see. So that we have a total of a budget of 26 electrons, because that's 18, 20, 26. So sulfur is going to be our central atom. And the first thing we need to do is attach all of our oxygens. This will cost 2 for 6 electrons to do, leaving us with 20 in the budget. So next we need to complete our octets. Let's go ahead and start with our oxygens. You'll notice that as it's drawn right now, each oxygen has access to 2 electrons. Each one needs a total of 8. So we need to add 6 to each oxygen. And if we go 1, 2, 3, 4, 5, 6, if we do this for all of them, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. We have enough electrons in the budget. And so that leaves 2. Oops. We've got 2 electrons left. If you look at our molecule, sulfur does not have a full octet. But we have 2 more electrons. So this rounds everything out. And that's it. So this is not technically not the final Lewis structure. But we weren't asked to determine the Lewis structure of the molecule. We were asked for the molecular geometry. But just for completeness sake, I do want to point out that that the best resonance structure for this molecule will actually remove one of the lone pairs, turn it into a double bond to minimize formal charge. So these 2 oxygens will have a formal charge of -1. So this is the best resonance structure for a molecule. But this problem, I guess, was asking for the molecular geometry of the central atom. And if we look at sulfur, sulfur has 3 atoms and 1 lone pair. So we have a total of 4 electron groups. So the electronic geometry is tetrahedral. Sorry, I'm running out of room there. So that's our electronic geometry, but the molecular geometry, to determine the molecular geometry, we have to look at the number of lone pairs that we have around our central atom. And because we have 1 lone pair, so we've got an electronic geometry that's tetrahedral. But the presence of 1 lone pair means that the molecular geometry is going to be trigonal pyramidal. So we have a, writing it out fully, trigonal pyramidal molecular geometry. Oh, gotcha. Totally. Oh, hang on, I can hear a 2-year-old incoming. Here, hang on 1 sec. Sorry about that. My 3-year-old just got up from his nap, and he didn't know I was in the middle of a stream. But he's downstairs now, and I'm back, so we're all good. Alrighty, yeah, let's do this. So ClF3. All right, so we got to do our hybridization. We need a Lewis structure. So we've got chlorine, which has 7 electrons, and fluorine, which also has 7. But we got 3 of them, so we got to multiply this by 3. So we've got 3 times 7 is 21, plus 7 is 28. Now, chlorine is going to be our central atom. Because it can make the most bonds. Remember, chlorine is on the 3rd period, so it's allowed to break the octet rule. So it can make more bonds than fluorine, because fluorine, being on the 2nd period, is never allowed to break the octet rule. So chlorine's in the center. Our first move is always to attach the ancillary atoms to the central. So this will be 2, 4, 6, leaving us with 22 electrons. Next, so each fluorine currently has access to 2 electrons. It needs a total of 8, so each fluorine needs 6 more. We've got 3 of them, right? So 3 orders of 6 means 18 electrons. And we have enough in the budget to complete all of their octets. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. All right. Beautiful. Beautifully done. Now, chlorine needs 2 more electrons. We have 2 electrons in the budget. But now this is where this problem gets interesting. After spending those 2 electrons, you'll notice that there are 2 more electrons in your budget. You're like, all my octets are fine. But here's the thing you got to remember. To draw the Lewis structure, you have to use all of the electrons. You can't go over budget, but you also can't go under budget. So what do we do with these 2 electrons? Not a normal problem to face. Well, we got to put them somewhere. So we have no electrons left over. And as we said before, chlorine's allowed to break the octet rule, so we're going to give chlorine an extra lone pair. All right? So chlorine in this molecule, I'm just going to scoot these over. I didn't really leave a lot of room. In this molecule, chlorine has 3 atoms attached and 2 lone pairs. So let's see. They want to know, okay, hybridization. So we have for chlorine, we have 3 atoms and 2 lone pairs, giving us a total of 5 electron groups. And the thing is, hybridization is 100% based on how many electron groups you have around your central atom. Because for each electron group, you need 1 orbital. So if you have 2 electron groups around your central atom, you'll be sp hybridized. If you have 3 electron groups, you'll be sp2 hybridized. If you have 4 electron groups, it'll be sp3. Now here we have 5. So our hybridization will be sp3, but then we need 1 more orbital because we have 1 more electron group, d. So we say that this molecule is sp3d hybridized. Okay, yeah, totally. I will sort this deal out. All right, so the regrade um, is complete. So everybody's getting credit. Now I just have to fix it in the problem bank. But the points have been sorted out. I don't know how fast it'll take to reflect on your end. All right. Okay, things should be totally good to go. Dude, you're so totally welcome. Thanks for bringing it to my attention as well. I appreciate it. great question here. So, okay. All right, so Julia, that is a an excellent question. All right, so it says okay, so question 59: which hybridization scheme allows for the formation of at least one pi bond? So I want to show you. So this is the Lewis structure for a molecule of ethylene, and I want to kind of get into how this pi bond how this double bond forms. Because a double bond is technically different than a pi bond. To show it, I'm going to rotate the orientation of this double bond. So right now it's parallel. I'm going to rotate it so that the CH bonds are coming out at you and then pointing back towards me. So drawing this thing in a little bit different perspective, kind of, again, rotated 90 degrees. I want to get into how this double bond forms. Well, first, the first bond between these two carbons forms when the sp2 hybrid orbital of one carbon overlaps with the sp2 hybrid orbital of the other carbon. So these two kind of overlap and create a space where the electrons are sandwiched in between the two nuclei. And that is the first bond here between these two carbons, the first bond of the double bond. The question is, where does the second bond in the double bond come from? And that second bond comes from unhybridized p orbitals. So there's a p orbital on each carbon. It is not hybridized, it is the atomic orbital. And something very special happens when those two unhybridized p orbitals are parallel to each other in space. They're not directly overlapping, but they're parallel to each other, and they start to blur together, both above and below the first bond that we formed between our two carbons. They blur together above and below, and they allow the electrons that were being held in each orbital to meet in the middle. So this, here in red, is the pi bond. And then right here in purple, this is the sigma bond. So anytime a double bond forms, and this is the critical part right here. One double bond is one sigma bond together with one pi bond. All right, that's what a double bond is made out of. Now, in this question, they're asking which hybridization scheme allows for the formation of at least one pi bond. Well, if we're talking about hybridization, if you talk about sp3 hybridization, sp3 hybridization uses all atomic orbitals. Uses all atomic orbitals in its hybridization. sp2 hybridization. This uses 1s and 2p orbitals, which means that there is one p orbital left over. And if there's a p orbital left over, that means you can form a pi bond. Because to form a pi bond, you need unhybridized p orbitals parallel to each other in space. So sp3 hybridization, remember there's 1s and 3 p orbitals. If you're using all of them together, you've got no p orbitals left over, no double bonds, no pi bonds are possible. But sp2, because it uses 1s and 2p, so you've got 4 orbitals total. But for hybridization, you've used 1s and 2p's. It means there's one unhybridized p orbital left over to line up with another unhybridized p orbital to form that pi bond. Alrighty, and so that is going to wrap up office hours for today. Thank you both, Julius, for coming in, making it